Alright, so here's the homework for writing polynomials, even though the homework here is actually a good review of all the different kind of polynomials that we've done. So using the rational zero theorem, just list the possible rational zeros. So for number 1, because the leading coefficient's 1, just look at the caboose. What are all the numbers that go into 40 evenly? So take your time. I'm going to make sure I don't make a mistake. So those are all the numbers that go into 40 evenly. 1, 2, 4, 5, 8, 10, 20, 40. Here we got to be careful because the leading number is 2 and not 1. So I'm still going to start with all the numbers that go into 28. Sure I have them all here. Then, no, 2 and 14, right? 14, then 28. All right, then, because the leading coefficient's 2, we have to divide everything by not just 1, but also by 2. So the ones that are odd numbers will also be on my list. See, 2 divided by 2 is 1. 4 divided by 2 is 2. It's already on my list. So the odd numbers, 7 over 2, is what I add to the list. So do you know how to create a rational zero theorem list that we could test using the remainder theorem or the factors theorem? All right, number 3. Given the possible number of positive and negative zeros using Descartes rule of signs. We didn't even talk about Descartes rule of signs. I kind of skipped it to go forward. It's a plus thing. Kind of cool, but kind of not necessary at this point. So these we are not going to do. Number 5. It says find all the zeros, then give the complete factorization of the function. So the first thing I look at is if it can be factored by grouping. And if I group it, it's not going to work. So I need to create a list. 1, 2, 3, and 6, and 7. See that 14, 21, and 42. So there's the list. Then I'm going to use synthetic division. Be careful if there's any missing powers. And then positive 1 doesn't work, so you go to the next one. Now it's not fair because I know the one that works, but you'd have to keep guessing and checking until you find the one that gives you a remainder of 0. So positive 3 gives you that. You're left with x squared plus 9x plus 14 equals 0. That's actually factorable. Two numbers that multiply to 14 and add to 9 are 7 and 2. So it says find all the zeros and do the complete factorization. So when I solve this, I get negative 7 and negative 2. So I know the zeros are 3, negative 7, and negative 2. The complete factorization then would be from the 3, you get x subtract 3, you get x plus 7, and you get x plus 2. Number 6. So we're going to create a list and then see what numbers work. So we got 1, 2, 3, 5, 6, 10, 15, 30, and then do the same thing over 2, so just the odd numbers. So 2, 3, 5, and 15. Then we test the list. So there's no short way around this. Because I already know the ones that work, it's not fair, but I'm going to go right to the ones that work. You have to do a treasure hunt. So the first 0 that works, this actually does add up to 0 if you add it up across. So positive 1 works, which is nice. And then the next one that works is negative 6. Now what's left over is 2x squared subtract 7x plus 5. That's actually factorable. So 2 times 5 is 10, and negative 7 The two numbers are negative 2 and negative 5. So take out the negative 7x and put in negative 2x and negative 5x. Then I'm going to factor out in 2x and factor out in negative 5. So I have x subtract 1 and 2x subtract 5. So let's put this all together. So the factors, positive 1, did positive 1 work a second time? It did work a second time. So I could have used 1 again, right? It doesn't matter. But I got, this gives me x minus 1, and I have another x minus 1, so we write down x minus 1 squared. Now if we're going to do the complete factorization, we can write it separately, x minus 1, x minus 1. And then negative 6 is x plus 6, and then we have 2x subtract 5. So the zeros, I don't need to write down. The positive 1 has a multiplicity of 2, negative 6, and then add 5 and divide by 2. All right, number 7. I first see if it can factor by grouping. So I'm going to factor out 3 and x squared and get 3x plus 1. Factor out a negative 5 and I get 3x plus 1. So they share 3x plus 1. We have x squared subtract 5. If I make that equal to 0 and solve it, they are both irrational, positive and negative 5. So I can write down the factors now. So the complete linear factorization, we have 3x plus 1, and then we have x subtract root 5 and x plus root 5, and then the zeros are negative 1/3, positive root 5, and negative root 5. Number 8. This is not going to be factored by grouping, so I need to create a list for 74. That's 1 and 2. 4 doesn't go into evenly. The next one actually is 37 and 74. So the list isn't that long. Do synthetic division. So 1 and 4, 41 and 74. Do a treasure hunt. 1 doesn't work. In fact, no positive numbers work because there's no sign changes. So negatives work. And if you try negative 1, that's good, but it's negative 2. That's the treasure. And then what's left over is x squared plus 2x plus 37. Not factorable. We're going to complete the square. So I'm going to subtract 37. To complete the square, you take 2 and you divide it by 2 and square it. So I'm going to add 1 to both sides. So the left side is x plus 1 squared, and on the right side I have negative 36. When I take the square root, the answer could be positive or negative. The square root of a negative number is imaginary, and the square root of 36 is 6. So subtract 1, and then you have your complex solutions. So to write the complete factorization, we're going to go x plus 2, that comes from that 0. And then we're going to write, don't make this mistake like I did once in class, subtract both of them. So subtract negative 1 plus 6i, and then x subtract negative 1 subtract 6i. And then the zeros are negative 2, negative 1 plus or minus 6i. All right, turn the page. Let's continue. Number 9, practicing it. So I first look at it as a trinomial. So two numbers that multiply to negative 48 and subtract to 8. So those two numbers are going to be positive 12 and negative 4. So 12 times negative 4 and 12 take away 4, they match. So if I take each factor equal to 0 and solve it, I know first of all the answer is positive or negative. I know it's imaginary because the square root of a negative number is imaginary. And then it would be the square root of 12. Now the square root of 12 can be reduced down. So 12 is 4 times 3, so the square root of 4 is 2, and what's left over is 3. The second one's going to be real. So if you add 4, the answer is positive or negative, and the square root of 4 is 2. We now can do the full linear factorization. So one's going to be x minus 2i root 3, x plus 2i root 3, x minus 2, x plus 2, and then the zeros we already found. So positive and negative 2, and then positive and negative 2i root 3. So two answers are rational and two answers are imaginary. Number 10. Number 10 is not factorable by grouping. So we're going to create a list. All the numbers that go into 48. That's a long list. Oh, the first thing I should always look at, is there a number that goes into everyone evenly? And there is. I can divide everything by 3. So I get x to the 4th. Alright, let me press pause on here.